I broke this into two integrals. I separated them, so that's going to be easier. This is the same as cosine of alpha t, according to Euler's theorem. So if I want to solve the first one, it's going to be 1 over 2, which is out, divided by, multiplied by minus 1 over s minus j alpha e to power same thing, negative t s minus j alpha plus negative 1 over s plus j alpha times e to power negative t s plus j alpha, where s changes from 0 to infinity. So this is basically this integral, and again, if you put infinity here, these become 0, and you can simplify this, and eventually you find this term. You can do this at home, but I just give you the final answer. So Laplace transform of cosine, we find it using the definition. So that's something which is like easily obtained using Euler's theory. You can do the same thing for sine of alpha. You can replace it to exponential format using Euler's theory and find the Laplace transform of sine of alpha t. I'm not going to do it here. The other two concepts that I want you to know, because we're going to use it very frequently in this chapter, is that if we have the Laplace transform of a function, if I know that the Laplace transform of f of t is capital Fs, then Laplace transform of f prime of t, it's going to be equal to s times Fs minus f0. This is f0 negative, or most of the time we assume that this is 0. So this is one thing that we're going to use very frequently in the course. Well, the whole thing is this thing, like you have the minus initial value, but most of the time we assume that this is 0. Excuse me. The other, and if you want to prove this, you can just prove it using the definition of Laplace transform. And if you want to find integral of f of t dt, Laplace transform of that, this is going to be 1 over s f of s. Right, so this is another concept we're going to use very frequently, especially when we want to talk about PID controller. We're going to work with integrals and derivatives, so I want you to remember this. And what if f of t is a constant? Or what if f of t is a unit function like this, which is like, it means like it's 0 before 0 negative and it's k after that. Again, you can find Laplace transform of that using the definition k e to power negative st dt, which is very easy to find. Then this is going to be minus k over s e to power negative st, where t is going to change from 0 to infinity, and for infinity this is 0, so it's going to be minus k over s times 0 minus 1, so it's going to be k over s. So if you take the Laplace transform of this one, it's gonna be k over s. So please remember constant or unit functions Laplace transform and exponential functions Laplace transform and derivative and integral. We're going to use them very often in the course. So that was just the first quick review of the concept of Laplace transform, which is a very useful tool to take us to frequency domain. Now, the other concept I want to talk about is the frequency response of a system. So most of the time we want to model a system. Let's say like this is a system. Sometimes we call it a plant. It takes an input and you're gonna have an output. Let's actually do I and O. Okay, this is output, input, output, input, output. Okay, so we are gonna convert everything to the frequency domain, and we want to find like the effect of this system on this input, and like what is the output coming out of the system. So usually we do this using a model that's called transfer function. So we find like how this system can be modeled in the frequency domain, and we want to see what is going to be the impact of the system on the input. So let's just like assume sinusoidal input. For example, let's just like do it like this. Okay, so this is our input, and let's say this is actually this is time. So like let's say like we have input like this, and let's say like we see the output, we measure the output, and it looks like this. Okay, so if you guys remember that we call this one the magnitude of the signal, so let's call this m of I, right? And this is like how much phase this sinusoid has, how much phase shift it has, right? So this is our input, and we have the same thing for our output. So m of output, the magnitude of output, and it has this much phase shift. So this is actually this is the phase. This is the phase of the output signal. I'm just doing it for a certain frequency. So this is like what's happening here. There's no change in the frequency here. They have like the same frequency, but their magnitude has been different. This is phase of input with the magnitude of input, phase of output, and the magnitude of output. So the transfer function is basically